All right. Hello, everyone. Thanks for coming to today's meeting for the Data Science at Georgia Tech CLEF group for 2024. This month, we're going to be talking about the modeling progress that's been done so far. Hopefully, everyone's gotten a chance to kind of play with the data and put them into some rudimentary models of some kind. There's roughly a month or two left of the competition, so we should start trying to build up models and trying to collect results into working notes. So the outline for today, I'll talk about some admin things, and then we'll go into the milestone presentations, and then we'll talk about next meeting, which is going to be our last one. So for the admin updates, I've added a couple of the following things. So here you can find links to the previous month presentations. All the presentations have also been recorded, and you can find those recordings in the index page. The second is that I've added a working note template. So if you are leading a project, you should start and copy this template or follow the instructions from the 2023 competition. But I've made it easy to just clone this and to go and start. A thing that I discovered very recently is that you can use VS Code with a plugin that lets you sync Overleaf to your local editor, and then you can use Copilot and Grammarly to write your documents. So it's real great. You can copy and paste tables and things into your document and then ask Copilot to rewrite it as a LaTeX table. Use Grammarly to make sure you don't have spelling mistakes. It's a really good workflow. So think about your working notes and make sure that you start them early so you're not rushing to finish them near the end of the submission deadlines. It might be good for us to do kind of an internal peer review. So think about having a draft ready before the submission deadlines. The third thing I want to talk about is these ongoing hack sessions. So we've had a couple of hack sessions over the last 3 weeks. They've been a lot of fun. They've been also kind of very productive sessions that tend to be kind of long. So for these hack sessions, I aim for them to be 8 hours continuous. We've had the last 3 weeks 2 8-hour sessions per weekend. So we've already had quite a few, almost I want to say 50 hours. Is that right? So there's a significant amount of work that can get done when you're in the same room with other people. Lots of just talking about the problem, being able to share your screen with other people. And so I think we've had about a dozen people come in and out of these meetings, and they've been super productive. So I'd encourage you to come to the next one, which is going to be this weekend on Saturday. Look out on your calendar for an invite to that meeting. And the final thing is just keep in mind your submission deadlines. So it's going to be different for every lab, but you'll want to make sure that you are ahead of the curve in terms of making your submissions and working notes. So with that, let's go into our updates. So for the first update, I'd like to pass things off to Ritesh to talk about IDPP.
All right, thanks, Anthony. Just a quick reminder on this challenge. We are given patients' data over here, and we are expected to predict their ALS FRS score, which is a score which highly correlates with the disease progression. So we are given a baseline score, and we are given a bunch of sensor data, and we are asked to tell, okay, we are giving you the time t sensor data until time n, time t plus n data, and you need to predict what will be their score at time t plus n. So that's the overall challenge. Our data set is extremely small, like literally small. It can sit on a floppy drive, as one of my coworkers said. But we have only 52 patients data provided to us, and after that, also a lot of patients do not have a complete data set. So there is a lot of NAN values, and apparently over doing research, we found out that this is pretty typical for EHR, like electronic health record data, because not many patients would want to share their data, and there are a lot of privacy reasons, and some of the diseases are very rare, so you don't have many patients to begin with, and things like that. So anyway, so coming to so we after doing a lot of EDA stuff like that, we decided what is the easiest thing to start with, which is a naive model. We just take the baseline score, like the previous score, and just boom, just paste it on the target score. That's it, right? I mean, and just see how it very well how it correlates, and apparently it did pretty good. We got a 0.62 RMSE just by using the baseline score and just doing nothing at all, and just giving it back the same score to the target value. So apparently that is good and bad. Good is we know that the baseline score is an extremely high correlated predictor of the target, and bad is now we have to beat this one to actually beat something better than this. So then we moved to classical machine learning models. The first one we tried was the fixed effects and the random effect ones, because patient data is usually have fixed effects and the individual patients random effects. And in the fixed effects, we tried multiple models from scikit-learn, random forest, gradient boosting, lasso, OLS. I mean, everything under the roof we tried. And the best one that best RMSE that we got was 0.55. And we have to actually, in our case, it's not a regression problem. We have to actually give integer values to the scores. So when we use it as a regression problem for prediction, our RMSE is actually better. But the moment we kind of round it up or down, our RMSE becomes even worse than before. So which is what is seen on the slide. So we have to find out how to make it into a classification problem without losing much of an RMSE error. We tried a new library, different libraries that we have not tried before. The TS-Fresh is one of them, which is used for extracting time series features. It extracts a lot of features, and we can use which ones are important, which ones are not, and put them in through the model. And for the random effects, we use the MRF model, the mixed effects random effects framework. Apparently did not give much improvement. So yeah, we did it, but not much of an improvement anyways. And over these exercises, we found out that sensor data that is provided to us has very little effect in improving our score. Baseline score seems to be the strongest predictor. So that information is there in the back of our mind always, that hey, sensor data may or may not improve much stuff. Yeah, so we want to go to the next slide, Anthony. Continuing there on the same journey, we had a task one. There are multiple tasks in this challenge. Task number one is using the scores that the patient is provided by the doctors, and task two is the scores that patient provides themselves for self-assessment. So we thought, okay, hey, you know what? Let's just try to merge the two data and see if we can get more patients now, because we have very less patients to begin with. We did that, but that kind of shrinks the amount of time. Like in the beginning, I mentioned we have to predict at time t plus n. It shrinks our n, and which does not correlate very well with our test data, which we are going to get. So we have that data, but we're still struggling to see if we're going to be able to make a good use out of it, because we don't want to squeeze our sequence lengths. We want to keep it similar to what the test data would be at. But just to make sure that the task one, task two data are coming from the same kind of distribution, we ran the chi-square divergence test to see if they are from the same distribution, and we found for the most part they came from the same distribution. For some of the patients, the data was kind of contradictory, but for the majority of them, it seemed it correlated pretty well. But here, also with using this one, we got an RMSE of 0.54, which was an improvement, obviously, from the naive model, but not as much as we had expected. Okay, so next slide, please. So finally, we moved on to the neural networks area, and since it's a time series type of work, we first tried the LSTM model. We provided it the sensor data, we provided it the baseline targets, and we tried to tell it to predict the targets. And here we got improvement over the previous ones. We have got about 0.52 to 0.53 RMSE. Tried hyperparameter tuning, did not help much. The issue is the data is so small it overfits extremely fast, right? Whatever, even the simplest of the simplest model overfits extremely fast. So we have to be very careful about overfitting. We try to add regularization to it. Nothing seemed to have much of an effect as such. And again, here also it was found that when we remove the sensor data, we did not deteriorate the RMSE by a whole lot. So again, proving our point, the sensor data was not very helpful in predicting. The baseline score was most of the time very helpful in predicting. So now knowing that the sensor data was not very helpful, we reached out and found out there is some other data sets out there from a website called ProACT, which ran very similar challenge few years back. And they have their scores available for a massive number of patients. So we're going to be planning to use that data set to see if we can train a pre-trained model, like a bigger model, and then use that model to on our data set to see if we can improve the score. So that's another try that we plan to do in the next few weeks. Next slide, please. Yeah, and then this is just a quick things we need to try. As I mentioned, ProACT is one of them. We want to try that one. We want to do an ensemble of two different models. One would be with the sensor data and static data, like the patient's weight, BMI, and all of that stuff, to see if we can cluster them together in some kind of a cluster. And the other would be coming just from purely the baseline scores. So and ensemble both of them in some kind of a weighted fashion, and see if we can, that will be a better predictor of the scores. And yeah, and the third point is the clustering. Yeah. So we want to see if we can cluster the patients, because every patient has their own trajectory. So we want to segment the patients. Again, we don't have many patients to segment, so we did not do it before. But at this point, we think there may be an opportunity here to see if we can segment the patients based on their trajectories, and then try to have a model for each group of patients, rather than one model for everybody. So that's another approach that we think we want to give it a shot. Yeah, so we have about 3 weeks. Our test data will be available end of May, and we have it only for 1 week. So in 1 week, we have to make all of our submissions for the task, and after 1 week, we are pretty much done. And after that, we have a few weeks for writing the paper and getting the leaderboard and seeing where we stand. We don't have a leaderboard while the test is running, while the test data is available. It's going to be only after the fact. So we don't know where we are standing while we are making the submissions. We will only come to know a few weeks after whether we were even close or no. So yeah, that's it from my side. Thank you.
Excellent. Thank you, Ritesh. Hopefully you get somewhere you do well. There's a lot of good work that's coming out of the IDPP group.
Yeah, it's an interesting one. It's a very interesting one. We thoroughly enjoyed it. I mean, although we're not getting that we want to do, but I think we have explored in a lot of different directions, and we learned a lot along the way. So it's been a very fruitful journey from a learning standpoint.
For sure. All right. Next, we have bird clay. For bird clay, I'll hand things off to Ashley.
Cool. So for bird clay, we started to add the bird call training data, which are 5-second clips from xenocanto.org, to a Label Studio project. So Label Studio is an open source data labeling platform. And how we're doing that is we're going to currently determine the primary and secondary call by manually annotating each call. And then we're going to feed the calls into Encodec and a classification model that establishes whether these recordings have a call or no call. It's because when we were thinking about using different models, and some of the bird localization models couldn't tell the difference between a call or a no call. So we wanted to have a primary step, or like a step before that, to determine whether there was a call or no call in each of the sound recordings. So if you go to the next slide, I took a brief screenshot of what the audio labeling task looks like. And we have, if you play it, actually I can share, I don't know if I can share my screen, because I was going to send the sound, but let me see.
And stop my share. That helps.
Can everyone see? Cool, this works now. So if you press this task, let me also see if I can share sound. Options to share sound. And then if I play this, you can see if there's a bird clip. I don't think there's a secondary call here. I'm not sure if my fellow bird play members would say, but primary call, if you press this, you can highlight here, and that would be the primary call. And we have about We're planning to manually annotate these, and then after we finish manual annotation, we're going to feed this. Let me reshare. Actually, Anthony, do you mind resharing the slides? Cool. And then we're going to feed these into encodec, and we're going to feed them into a classification model after we compress the data. To explain encodec, I'll pass it off to Adrian.
So for encodec, we continued our work looking into the embeddings. We found that splitting into 1 second chunks works. And what that means is if we split the audio files and then embed these audio files and then reconstruct this, this is the same thing as, let's say, doing 5-second intervals. Like we can, it's time invariant in this way. So we can split into 1 second chunks to feed into our classification model. And then we looked into some visualization with UMAP and something called PackMap, which is UMAP, but with better global location of the features. And here you can see this is just three of the species, and each point is a 1 second interval. Obviously, it's not great because those 1 second intervals have not been like pre-processed or anything by like call or no call. So there is definitely a lot of overlap. And our next steps with encodec is embedding all the recordings into one Parquet file with the help of Luigi. And then we're going to feed these embeddings into our call and no call model.
Excellent. Thank you, Ashley and Adrian. I'm super excited about both having Label Studio set up and being able to actually build a labeled data set that we can quantify things, because there's no real labels in the task. And then it's super cool to be able to use a transformer-based model for actually doing some of the transfer learning tasks that are necessary for BirdClay. So super excited for the work, and Adrian and Ashley have definitely been pulling their weight. So next is GeoLifePlay, and I'll talk a little bit about GeoLifePlay. The slides are pretty dense, but I'll try to go through the big ideas. So I've been mostly working on trying to get an initial submission to GeoLifePlay. Mark has been working on some of the data ingestion work necessary for computing these tile embeddings using TileDevec. And Elmo has been helping with building features using the time series data that we have from the competition. So some of the challenges that we've faced in building an initial model for GeoLifePlay is that the number of classes in GeoLifePlay is pretty large. So the task is to classify these survey sites, and these survey sites are located across Europe. And the goal is for a particular survey site, what species might occur in that location. There's almost 4 million of these survey sites, and there's roughly 5 million data points. So there's on average, more than one species per site. There's also about 10,000 species. So if we try to build a very simple logistic regression model where we use the latitude and longitude projected into a Euclidean space using meters as resolution, if we have just the latitude and longitude predicting one of 10,000 classes, we find that this is not a scalable training process. I ran a machine for almost 3 days before killing it because it was taking forever in order to train a logistic regression by stochastic gradient descent. So this can be considered an extreme multi-label problem, and this is one of the big challenges here. So I've decided to go towards a nearest neighbor approach in order to build this initial model. A survey site is going to have species that occur within a radius of that site. And using this methodology, we can computationally build a model that can predict species. But we can do a lot of things with a nearest neighbor model. We can build actually k-nearest neighbor graphs. And with these graphs, we can learn embeddings of the graphs. Embeddings are just like it's basically a lookup table of nodes in a way where the lookup tables return a vector, and those vectors are able to tell how similar the nodes are to each other. The way that we would build this embedding is with NodeVec, and there are a lot of challenges here. The species embedding is doable because that's a 10,000 by 10,000 node graph with a couple 100,000 edges. But the survey to species embedding is really expensive. It has, 4 million nodes and between 10 to 100 million edges. So very, very challenging to build an embedding here. So with this, I think the approaches that come next are kind of as follows. First is to build that very simple KNN based model where we find the nearest neighbors, find the nearest species that occur within a location of a survey site, and then we manually figure out what the threshold is for the distance to include a species occurring in that site. I think this is going to be relatively easy to compute since we already have all the data in one data set. The second is to kind of reduce the problem down a bit. So instead of doing a logistic regression on 10,000 classes, what we can do is instead learn a regression from our features into a reduced or low rank label space. And when we learn this relationship between the features and the low rank space, we can project the labels out back into the original space. So we may have, say, 100 dimensions for our label space, and then we project back out to 10,000. And then we do some quantization. So it might just be keep all the labels that are above a threshold. I think a second iteration of that is to use the NodeVec embeddings and to use k-niche neighbors instead to quantize. And this is going to have a lot more information than just doing PCA. So once we figure out how to do this multi-label problem with lots and lots of labels, I think what we do next is to do some feature engineering. So we have the DCT of the discrete cosine transform, which is a compressed version of our features, which are tiles of rasters and time series. And once we get those very simplified tile features down, I think it'd be interesting to incorporate these like contrastive embeddings of the tiles. And then finally, I think it would be really interesting to do some feature engineering that uses graph theoretic measures. So we have this k-nearest neighbor graph. So we can kind of propagate information across different survey sites through the species that co-occur in different sites. So we can build new feature vectors that take in first order and second order information that just get propagated along in this graph. We might just do the NodeVec embeddings. You just concatenate or average the species NodeVec vectors, but we can also propagate information about the local environment. So this is GeoLifeClay. There's a lot of work to be done, but I think this is a really interesting problem that takes into account takes into account biodiversity and lots of really challenging problems in terms of computation and computer vision and a little bit of network science. So that is GeoLifeClay. Next is PlantClay. And for this, I'd like to hand things off to Murillo.
Yeah, thanks, Anthony. So today we'll be talking about PlantClay. This is just a recap or an overview of the entire pipeline that we have so far. So we can divide the pipeline into 3 subsets or 3 sections or 3 stages. into downloading, pre-processing, and modeling. So downloading, pretty straightforward, downloading all the images into a GCS bucket. The pre-processing one, it's quite interesting. We're doing a lot of pre-processing and data transformations until we get a very clean and nice data set, which I'm going to be talking about two of those pre-processing pipelines in the next slides. And also we have a modeling phase, which we are converting the images into embeddings and then doing some dimensionality reduction using the DCT algorithm. And then we put a classifier at the end so we can get the classifications. And keep in mind, the biggest challenge that we have for Plain Clay is the difference between tasks for the training images and the test images. Training images, all of them are single label, while the test images are multi-label. So that's going to be a significant challenge that we're trying to overcome right now. Next slide. So here's the pre-processing pipeline for the crop and resize. So the original data set has about 1.4 million images. And on the left, you can see some of those examples of the images on the original format. And after we put the images through this pipeline, we reduce the dimensionality of the images and we also crop them to be squares. So we were able to basically reduce the data set size from 290 gigabytes all the way to 15 gigabytes of data. And that's a little bit more than an entire order of magnitude in reduction. So this is one of the pipelines. Next one. So after the images were cropped and resized into squares, so we pass them through Dino V2, which is a vision transformer model created by Meta. And we get those embeddings that you can see on the left side, which really just looks like a bunch of great things. Those are just the visual representations of the embeddings. And then after that, we pass the embeddings through the DCT, which is a dimensionality reduction algorithm that you can think of it in the same family as a PCA, but the DCT is actually comes from Fourier transforms. And it has some really nice properties, especially for compressing images. So as you can see, it creates all of those really interesting formats. You're probably looking at the first row of every single image. It looks a little bit different, and it's just how the algorithm is compressing the images and represents the information. And then, yeah, you can go to the next slide. Oh, would you mind sharing again, Anthony? Like exiting and
Yes. Oop, let me. How do I do this? Refresh. That is not what I want. This is the, can you see my screen though?
yeah. Can
Okay.
you come back? Yeah, there you go. So I just wanted to reiterate the difference between the tasks that we're trying to accomplish. So on the left, you have the single label images. And on the right, you have some of the task images. And some of those images, I'm not sure which one, but at least one of them on the task data, there were up to 8 different species of plants on the same image. I'm not even sure how many species are on those images, since they didn't really make available the labels for the test images. But so this is basically the main problem we're trying to solve. There's another pipeline that I did not show that we're currently working on, which is a pipeline to generate collages of images. So we're going to be basically creating a collage of 3x3 or 4x4, maybe up to 8x8 images of those of the images like in a collage. And that's going to be the data set, and we're going to feed into the modeling pipeline to extract the embeddings from those data sets and also go through DCT and then a classifier at the end to make the classification of multi-label to multi-label. And yeah, that's basically everything.
Great. Am I unmuted?
Yeah.
Okay. Great. Thanks, Marlo. It's great to see the pipeline working. So I'm excited to see how the modeling goes. That seems super challenging. All right, so next is going to be Fungi Clay, and Max is the person who put the slides together for today, and I'll be presenting them. For Fungi Clay, the group they've built a roadmap for the upcoming weeks. So Max, Teresa, and Chris are all part of a deep learning group, and they're using this as their final project. So very similar to the way that Plant Clay and Snake Clay are going to be doing things. They built a pipeline to embed all their training data into V2, Dino V2. And for some of the things that they have coming up, they want to build a couple other embedding models and incorporate it into the workflow. So one is to use ResNet, and the second is to use, which is a very simple baseline, and the second is to use CLEF, which is a multimodal model to incorporate both information about the images and all the metadata associated with the images. They're also going to build a custom loss function, which takes into account misclassification of poisonous species, and then just run the entire modeling pipeline against all the combinations of these things. So I think at the end of their class, they'll have a really interesting comparison of the different methodologies, and this will be a really good foundation for the competition. So that is Fungi Clay. Next, we have Snake Clay. So Marilla, do you want to do this one?
I think Ryan is gonna be talking about it.
Oh,
Is
is
he?
Ryan here?
not- Okay, he's not here. So yeah, no, I can talk about it. So for Snake Clay, we're actually gonna be leveraging a lot of the pipeline that was developed for Plant Clay. And Ryan, that is in your group, he actually has, well, he's very passionate about snakes, and he even has a pet python. So right now, we are in the process of actually developing a subset data, basically a curated data set of snake species that they look similar to each other, but they're not the same. Mostly because there's some of them are venomous and some are non-venomous. So as Ryan wrote here in this slide, so there's a featuring and visualizing aspect to the notebook that we are building for that. And we're creating the subset of the snakes that Ryan identified as being similar, even though they're not the same species. And then we're hoping to get from that just a really nice baseline to compare. And also, we're probably going to be generating plots like UMAP plots to actually visualize those species in a lower dimensional space. And yeah, that's what we've been doing so far.
Awesome. Thank you, Murillo, and thanks to Ryan for putting together the slides. I'm stoked that we have somebody who's like really into snakes.
Yeah.
Cool. Now for Pan, is Ben here?
Yeah, I'm here, Anthony.
Excellent.
Not too many updates from Pan on the modeling side as opposed to last time. I can give a refresh on what we've done and our plan for the future and some basic accuracies, but the slides are pretty much recycled from the previous meeting. So as a refresher, the Pan group is our task is trying to discriminate between human and AI text. And this is a fairly new competition. The competition committee released a very small data set. So we've collected a bunch of other data sets from like Hugging Face and other areas to kind of create our own test set. And there's 3 team members, me, Abhinav, and Jack. And we're each taking a different approach to discriminating between the human and AI text. And we're at the point where we're kind of fine tuning our own individual approaches and we're going to ensemble them at the end. But if you go to the next slide, I can kind of, again, just sort of go through what the approaches were. So my approach is this entity graph approach. It's based off a paper that was published a few years ago that kind of tries to model the factual coherence of a document So just trying to go quickly through this. You have a document. You will take 2 data streams from it, or 3 actually. You'll take the classification token from a Roberta embedding. You will create a next sentence prediction model from BERT that just kind of takes 2 sentences and tells you like with what kind of percentage that one sentence like coherently follows the next. And then finally, we'll break the document into individual sentences, piece out the entities from each sentence, and then try to create edges in a graph between each sentence. The entities is like kind of the meat of this approach. We take Roberta classification tokens of these entities. We're trying to incorporate like the Wikipedia 2 vec embeddings on top of it as kind of that factual piece. Create a graph neural network that kind of takes convolutions between the edges of each entity, and then take like an average sentence representation of these entities and feed it into an LSTM, and then multiply it by the next sentence predictions to kind of create like a weighting on each sort of average sentence representation, and then finally concatenate that with the like semantic essence of the text from the Roberta classification token and output a prediction. There's been a lot of pre-processing issues with this approach. Getting everything to work in like a timely manner has been difficult. I finally got it to start, kind of rolling through quickly. Some very early accuracies I've gotten on this model have been kind of in like the 60% range, but that's only on like 1,000 samples trained for like 10 epochs. So I feel confident that that could get a good bit higher with some more fine tuning. So if you want to go to the next slide, I think this might be Abanov's approach. So Abanov's approach is to take a BERT model, fine tune the parameters with like a LoRa approach, and you can just sort of his approach is very similar with like the BERT sequencer classification, but he effectively takes like a embedding of the matrix of the document, feeds it through like a BERT style model, and then gets an predicted output. And so finally, Jack's approach is also very similar to mine, except for his. He is taking the neural dependency of the graph, which he tries to build a different type of edge between each word. So he'll use like NLP, one of the spacey models, to create dependency graph. There's an example right there where you can see that like prefer and flight have a determinate object relationship, where the and flight have a determinate relationship, and he's building a graph across each document like that to again create a model that predicts human versus AI text. He's gotten very good accuracy. I think his has been in the high 90s. But the caveat to that is that he's been training on only a data set from Wikipedia, and the embeddings he uses for his, nodes, I suppose, are Wikipedia 2 vec embeddings. So we're kind of holding out and seeing what that accuracy will look like once he's put in more data sets that aren't Wikipedia, to see how those embeddings work. But our sorry, so there's just gonna riff on like the ensemble approach. So the competition is the way that the data set is processed is that they actually give you a pair of texts, and you have to discriminate between which one is the human and which one is the AI. We're still kicking around the best way to do that. I know Abanov has tried to train his model to take 2 at a time as opposed to just 1, but his accuracy it took a large hit trying to do that. So I think what we're trying to do is to take both texts, put them separately into each model, and then have an XGBoost meta classifier trained on each one. And then we'll probably have some sort of rules-based decision where whichever one has the higher probability gets donated an AI text. And if the accuracies are close enough, we'll probably give like a 0.5 designation, which basically means this is too tough to tell, because the way that the competition is set up is that they're trying to dissuade you from just taking random guesses. But that's it for Pan at the moment. So Touche has so the past month, the last time we were together, we tried to implement this like contrastive attention network to kind of create these embeddings. It really didn't work out too well, so we're just going to try and focus on like the clip embeddings. So basically, as a refresher for the Touche competition, we're given an index crawl of Google query searches from the competition. It ends up being about 6,600 images. We're also given a set of arguments, and our job is to find the most relevant images to that argument. And so our approach has been to take the 6,600 image corpus, create an image embedding from CLIP, and we're also given text embeddings from or we're also given image descriptions from some sort of VLLM that they've worked on each image. And so we kind of create this combined embedding of like 70% the image and 30% the image description, and feed that into like a Chroma D vector database. And what we've done so far is to take like a clip embedding of the argument and then have it retrieve, the top K samples from our database based off of cosine similarity. So on the next slide, I actually have an example of what that looks like. So to the right here, like one of the arguments is abolishing the monarchy would encourage more democratic principles and equality among citizens. And so with this approach, here's like the top 5 images that we get. It's sorted in order of cosine similarity, but you can kind of see that they're all pretty relevant for the most part, right? Like every image kind of has like abolish or the monarchy in the image, right? So clip on its own has been pretty decent. The last thing we want to try is sort of this re-ranking mechanism. So in the competition, you are kind of dissuaded from pulling together images that can kind of be used across a lot of different arguments. And so there's like 2 approaches that we want to try, which is number 1, once we've taken our top K samples, we then run each one through Lava, which is a multimodal LLM, to create kind of an image description relevant to the argument that we're talking about. So for example, we would take like, the first image and prompt the Lava model with, how relevant is this image to this prompt, give supporting reasons why. And it would generate a text description for each image. And then we could probably use another LLM with another prompting technique to then rank those texts to try and see if maybe that provides possibly a more accurate reading on the samples returned. The second approach is to continue with the clip embeddings, but we'd probably have to add some sort of custom loss function, as I was saying earlier, to dissuade from ranking images that would also have high correlation to other images, because part of the competition is trying to get very targeted specific images for that argument and to not use like very blanket general images that you can kind of apply each argument to, but are very vanilla in that sense. So that's everything Touche has been working on as well.
Excellent. Thank you, Ben. Next, I'll hand things over to David to present about eRisk.
Hello, everyone. So eRisk competition is mostly over. Task 1 was submitted 2 weeks ago or 1 week ago, and Task 2 was just submitted today. Task 3. The competition officially ends tomorrow, so it's basically done. But thanks to Anthony, we worked over the hack sessions, and we were able to build a pipeline that we can see in the chart. Mostly the work what we did is like pull the data, we converted it to Parquet so that we could process it faster using Spark. And we use TF-IDF and to find the sentences that were more relevant to the 21 symptoms of depression. Recall that on previous presentations we were working with the depression symptoms questionnaire. So that's the summary of that we're doing with this task. I particularly use the sentence transformer model to get the embeddings, and we later use a heuristic regression to do a supervised learning approach to solve this task. We can move to the next slide. In here we can see some of the results of the different models that we used. So we not only use the sentence transformers, we also use Word2Vec and naive-Bayes analysis, naive-Bayes. We can see that the transformers is the best performing in the mean accuracy test, and as the same with F1 score. One of the challenges that we had is that when we work with transformers, the time for getting that those embeddings was kind of untractable, so we had to do some reprocessing and filtering of the sentences, because otherwise we would have been waiting for a long time and not be unable to submit. But we did that, and we finally submitted the most relevant scores to the FTP server that they had for submittal. Okay, let's move to the next one. Okay, this is Arian's work. He's not here right now, but as you can see, we're also working with sentences from social media. This is task 3. Let's recall that is related to symptoms of what was this one? Eating disorders. Yes. So what we did here is like we transformed the XML data that contained the posts from the social media into JSON, and then we did some text preprocessing, removing characters that were unreadable, stuff like that. And we also used BERT embeddings for this one. Arian's analysis was that he did a prediction using the embeddings. It had 700 features, but he also used dimensionality reduction and reduced that to 50. And he compared and contrasted those two results, and we can see the results on the next slide. Yeah, so there's like a comparison right there on different models and doing the dimensionality reductions, and then after and without the dimensionality reduction. And as far as that goes, that's all we have for ERISC. The next thing we're doing is we're gonna work on the paper. So we have to figure that out. That's the next thing we're gonna do. Thank you.
Congratulations on finishing. So it's exciting. It's exciting to have groups come over the finish line. So definitely make sure to be aware of when the task deadlines are. Next, we'll have Wenshin presenting about BioAsk. Wenshin?
Okay. Can you guys hear me?
Yep.
Okay. So BioAsk is a competition for medical question answering and information retrieval. So the task we are given is that given a question, our assistant should return a list of relevant articles and snippets from the PubMed, and also generates a exact and an ideal answer. Today I'll talk about the results we just got back from Task Synergy 2024, which took place in February, and then I'll talk about the improvements we're recently making for task 12B on top of the model we built for the synergy task. Next slide. So this is the leaderboard link to the round 4 of the synergy task, and we submit 5 systems to the competition, and for here, system 1 uses the SPACY biomedical name entity recognition model for keyword extraction, which builds up a query to the PubMed database, and then it uses the Mistral 7B language model for question answering. Here, the prompt we sent to the LLM has no context, and the system 2 to 5 are similar in terms of the algorithm used, and then the differences is that the LLM model being used are different. And for the keyword extraction part for the information retrieval, we use the LLM composed of use the LLM and a few short examples in the prompt. And then for the question answering, we added the context, which use the snippets from the information retrieval part to compose the query to the LLM. And yeah, so we tried all the different models that's offered by the TextThings website. So Mistral family model and Lemma and GPTJ. Next slide. So this slide shows the information retrieval results for Synergy, and for the document retrieval, the best performing system is not our system, and it has 0.15 map score, and our system, our best system is Mistral 47B, which only has 4% on the map score, and then similarly the snippet retrieval accuracy are 3% for our system and 10% for the best performing system. So so there's a lot of rooms for us to improve. And then for this model we submit to Synergy, we only implemented a very basic information retrieval algorithm, which only sends a query to PubMed to retrieve 10 records and use that 10 records as our response. But we're now thinking about doing, and we also already plan to do 2-level information retrieval, and we'll see if that will help. And then in terms of comparing all our systems, the conclusion we get is that the Mistral family system seems to perform much better than the other ones in terms of the keyword extraction task. Yeah, that's it for this slide. And next one. So this slide is for the test results for exact answer generation. Our best performing system got 62% F1 score on yes or no question. This is binary answer question, and then for the factoid question it's 31%, and then for this question it's 22%. Here we can see the Mistral model still continue to outperform others, and when we look at the Mistral 7B with context and without context results, we can tell that the with context generally improve the accuracy much better than the no context one. The next slide. So this one is for the ideal answers. So our total score, so this is ideal answer, which is a long form answer, and it's not graded by a system. The organizer have to manually reviewing each answer and give a score on readability, recall, precision, and repetition. And our best performances and actually retrieve really close score to the best one. And yeah, this is very promising. And the other data I didn't show is that they have an automatic score. It looks like our automatic score are much lower than the other system. However, our manual scores are higher than the other system. So we're gonna there's probably some interesting insight we can draw from that. And the other thing to note is that the Lemma 2 model here is really not performing good, although I think it was on par with the Mistral 7B in terms of the other task, but here it's really not as good. So I'm planning to look into the actual output we generate and see why it's not what is falling short at. That's it for this one. And then next slide. So now I'll talk about the improvements we are making right now. For the information retrieval part, we added some mechanisms for resampling and fallback, because as we all know, the LLMs are non-deterministic. Sometimes if you do a couple rounds, they will give you a good answer if the first few ones are giving really noisy information. So we added the retry mechanism. We also added the OpenAI model into our experiments. So for this one, we are using instruction to as we are composing instruction instead of the vanilla few-shot learning to prompt the model to directly return the PubMed query. And currently our best performing system is still using keyword extraction instead of asking the LLM for a query. And then the Mistral 74B is currently at 8% F1 score for document retrieval. Yeah, that's it for this one. And then next slide is for the QA side of improvements. So I was mainly focusing on improving the scores for exact answer. So like previous one, I also added a few resampling for the yes or no questions generation, and then also add some conditions to detect if we are getting a bad LLM output. For example, if the answers doesn't return yes or no, that's a really bad answer. And also if the ideal answer is really short, we will ask it to regenerate. We also, instead of using one fixed snippet for the context, we are composing different contexts and increase the variability of those contexts by picking and then combining from different snippets. And this one actually gets us, we're running this on a training data set, which associated with 11B, which is a competition competition data set happened last year. And we are able to get 100% F1 score on one of the round with Mistral 47B model. Next slide. Yeah, so this is for the factorial and list question improvements. For factorial question, we switched to use a prompt that, so originally we used a prompt that composed of 1,000 characters from the golden snippets. Now we are switching it to use only one golden snippet, which surprisingly improved the results. And also we switched to 74B model, which is a larger model. And now the accuracy is 81%. Then for list question, we're also like before composing, increasing the variety of the context in the prompt, and also grouping the synonyms in the list question so that we can improve the precision of the results, which indirectly improve the L1 score. So 31% is the best we got so far. Yeah, we still have 2 more rounds for 12B, so we are hoping to improving those and get ahead of the leaderboard. I think that's it for my part.
Excellent, excellent mention. Yeah, this is super exciting. First group to get back results. I think this is these are really great results. Yeah, I'm impressed. And finally, we have long eval. So for long eval, I'd like to give the stage to Joshua.
Hi, everyone. So I'll be presenting for long eval task 1, and for task 2, Luis is working on task 2, but he wasn't able to be here because of work. So I'll be here kind of going through that stuff. So for task 1, like I said before, our implementation is simply a built on top of Elasticsearch. So we're ingesting our training documents into Elasticsearch. We are and then we are passing in our queries, our test queries, and we're running them and saying, hey, how relevant can we get this search engine to work? We're doing that using Python. And yeah, really simple. So the part where it gets a little bit wonky and a little bit fun is where we start to use vector embeddings, and essentially performing a vector search, utilizing different ways of generating embeddings. So the default way of vectorizing text passed into Elasticsearch is typically using the sentence transformer. We used all mini here. We used the all mini model, mini 16 model, and that provided us with, I think, our most optimal average and CDG. After that, we tested out word2vec and glove as methods of generating embeddings. Surprisingly, glove performed the worst, whereas I thought being context independent might. But if you think about it, it kind of makes sense from a intuition standpoint. Glove is probably the most context independent of the group of those. So yeah. So in the future, for our future research, next slide. We need to go ahead and run the search with a temporally distant queries, and then calculate the change in average NCDG scores so we can kind of focus in on which method works the best over temporal distance. And then there's some other essentially we've kind of like narrowed, using Elasticsearch has allowed us to narrow down our the variable that we're kind of testing to really just the embeddings of figuring out, hey, which embedding ranks relevant documents the best over temporally distant data, right? So there's a few different embeddings that we want to use. We want to use traditional NLP methods that are context independent, such as bag of words, TF-IDF. We want to use context dependent and transformer-based methods, such as BERT and XLM, which is a BERT-like model. And then we want to use context-dependent RNN models, which I thought was very interesting. Elmo, I think, could become our our front runner as far as performance wise because of its context dependent nature. I would also like to see how well the context dependent and context independent methods perform against each other as far as being temporally distant, just because, again, just intuition, the assumption is that a context independent method would work better than a context dependent method, since the context of the actual sentences and words may change over time. The assumption. Um, and we'd love to see if that's correct. So yeah, that's the analysis that we have currently. We're just about ready to submit our first model. It still hasn't released yet. I'm in long eval Slack right now. Like the actual like Slack for the conference, the workshop. And they're like, everyone's like pestering them, like, hey, what's going on? It's been 2 weeks. The last we heard was it was gonna be 2 weeks, and that was 2 weeks ago. But good for us because we are not exactly ready to submit for task 1 just yet, since we still need to test on the temporally distant queries. But we'll probably do that this Saturday at at our hackathon. So for task 2 is a sentiment analysis task that Luis that me and Luis are working on together. We some of the first part of what we were doing was, okay, let's just stick with bag of words and TF-IDF, and then slap a base model and an XG boost model, and let's run from there. What we figured out was that the glove vectorization was a better choice as far as staying power over the 2 years. The model tests on data from, I think, 2014, which is the non-temporally F1 performance, then 2016, and then 2018. And we need to test on the full data set, where, like we were talking about before, we need to concatenate that data set, we need to concatenate those 3 data sets into one, and then test the models on that entire data set. But as you can see right here, XG Boost did a great job of not decreasing performance. And we really think that it was because of the context independentness of glove. We also introduced a multinomial regression model that I think Luis is very, very proud of for getting trained. It did not do as well as XG Boost, sadly. So, yeah. I just updated with the non-temporally F1 performance one. It was 0.72. I couldn't find the numbers for a minute. So our immediate analysis for the task, like I said, XG Boost were able to mitigate loss in performance over temporal distance. Really think the reason for that is because we use context independent method of generating embeddings. We're going to test that intuition, and we're going to purposely use context dependent methods of vectorization, and kind of see what happens. And we're gonna test one variable, and we're gonna really focus on the text embeddings. We're gonna keep the models the same. It's really just gonna be those 3 models, and yeah. So yeah, right now that's kind of our march forward. Is for both of these tasks, we're gonna see how the text embeddings changes, how the text embeddings and their dependence on the context of the words affect the ability of the model to stay temporally persistent.
Excellent. Thank
Yep.
you very much, Joshua. This is looking very promising. I'm excited. I'm excited that you've gotten Elasticsearch to work so well.
I love Elasticsearch. I'm telling you, I'm gonna get a job there. It's gonna happen. I'm saying it right now.
you know, I have mixed feelings about Elasticsearch, but it is a very good tool. Great. So that is the end of all of our milestone presentations. So I think there's a lot of good progress. We have teams that have gone over the finish line. We have teams that are still going in progress, and I think that this is really cool. So with that, our next meeting is going to be our last meeting. I think at the last meeting, we took a vote and we decided that we would have one more meeting after the semester is over. So this is going to be on May 9th, which is the second Thursday of May. And this is going to be after the semester is done. So until then, best of luck on your projects, and hopefully we'll have a really good turnout at the conference next year. So that is all for this. Any thoughts, questions, concerns? Excellent. Then I'll stop the recording.